Okay, how many points does it take to make a secant line?
2.
How many points does it take to make a tangent line? 1. Okay. Oh, great. Okay. All right. Yeah, and that's a bummer because the regular calculus, like AB calculus, isn't even there yet, and like Mrs. Price's calculus class isn't even going to get there till like October. So he's probably trying to teach stuff that people, but you guys all know it already. All right, so we have a secant line, secant slope. Newton and Leibniz defined it similarly, but they used different notation. Newton said that secant slope was f of x plus h minus f of x over x plus h minus x. So that's y2 minus y1 over x2 minus x1. So that was how Newton did it. He called his points f of x and f of x plus h, and they were right next to each other because h is not a big number. He simplified it, of course, the denominator, and so it would be written as f of x plus h minus f of x just over plain old h because the x's cancel out. So that was how Newton defined secant slope, the slope between two different points. Leibniz was a little bit more traditional. He defined it as f of b minus f of a over b minus a. So that was his y2 minus y1 over x2 minus x1. So those are the secant slopes. To get from a secant slope to a tangent slope, the points have to be so close together that they're practically on top of each other. So if you're looking at any old curve, and here was your x, and here was your x plus h, h is really big in that sense. H is very far away. But if you slide that a little closer, and that's now x plus h1, and you slide that a little closer, x plus h2, and you just keep moving the points closer and closer together to each other. And x plus h4. Eventually, the points will be on top of each other because they're so close. So how big is h? Is it big or is it small? Okay, how big is h? It's not big at all. How small is h? Really small. How small? Infinitesimally small. How small? Approaching what? Approaching 0. We want h to approach 0 so that these dots get closer and closer until they are practically right on top of each other. And that is the conversion of secant slope to tangent slope by having them be so close. All right, so we're going to now move from the definition of secant slope to the definition of tangent slope. And the difference, what makes it a tangent slope, is the limit in front of it that shows that h approaches 0. And that is what makes it different. If you don't have the limit written there, it's not a tangent. It's still a secant. Because if you don't have limit, then the 2 points are distinct, and that would be a secant slope. But by having the limit and having that h value approach 0, you've now converted it to a tangent slope. All right, so the only difference is that Leibniz, then, of all of these things, he was calling his things A and B. All right, so all these X's and H's and everything, they were just his, Leibniz called them A and B. So he said we're starting at A and ending at B, And then I'll move it closer and call that B1, and I'll call that B2, and I'll call that B3, and I'll just keep moving closer and closer. And so his wasn't an H that was approaching 0. His was a B that was approaching what? B was approaching A, right? And so then the other way to write that is in Leibniz's, and he said B was approaching A of f of B minus f of A over B minus A. And eventually, they got sick of calling this the tangent slope, the tangent slope, the tangent slope, so they coined the phrase the derivative, which is essentially the value of a tangent slope. Okay, so you have to pretend that you don't know anything about derivative rules right now. Okay? We're going to have to actually prove the derivatives. It makes you appreciate the derivative rules that you do know by knowing how to prove it. All right, so let's do it this way. Find the tangent to the following function to f of x equals, let's do x cubed, or x squared plus 2x at the value of x being equal to 3. So we're going to find that tangent. Now, you know what the answer is going to be if you remember your derivative rules. But what I'm asking you to do in this one is to prove it for one day. For one day, this chapter, we have to prove our derivatives. When we get to chapter 3, which will be on Wednesday next week, you can use your derivative rules very happily. Okay, this is a polynomial. Newton, his formula favors polynomials, so we're going to go with him on this one. Leibniz's favors more powers and square roots, things like that. But Newton was great for, you could do either. You really can pick either. All right, I'm going to stick with Newton. And so I'm going to say, all right, let's find the limit as h approaches 0 of. Now I want f of x plus h. So I need to replace all the x's with x plus h. And then I have to subtract just the function itself, so x squared minus 2x. And that whole thing is over h. So for this homework, you're going to have to prove it the long way. So make sure you're good about your equal signs. Make sure you're good about using the limit notation. You drop the limit notation, it's not tangent anymore. And so then we'll expand. We'll have x squared plus 2xh plus h squared plus 2x plus 2h minus x squared minus 2x. And all of that should really nicely clean up for us algebraically. That's why Newton's thing always works really nice with polynomials. So we can tell that what's going to cancel? X squareds and the 2x's. So that's going to leave me with 2xh. It's going to leave me with h squared and 2h all over h. So what do all of those terms have in common? An h. And so we can reduce this by h, which leaves me with 2x plus h plus 2. And then we can substitute in 0, 2x plus 0 plus 2. And so the tangent is 2x plus 2. I want the specific value of the tangent at the point 3. So then the slope of the tangent, which will be m, will be 2 times 3 plus 2, or 8. All right, let's suppose that the same example, this is going to be the example continued. Write a normal line. Now in math, normal doesn't mean like regular people, normal people. What does normal mean? Not tangent. It doesn't mean secant either. It means perpendicular, right? Normal means perpendicular. And so for a normal line, we want the slope of a perpendicular. So we indicate that with the m with a little perpendicular symbol underneath, which is like an upside down T. So what will the perpendicular slope be? negative 1/8. And the point we want to go through is the point 3 something. Now x was 3. Let's look back at the original function because I'm just continuing. What's the value of y when x is 3 in this function? 15, okay? So we want the point 315. So the normal line would be y minus 15, the perpendicular normal slope of negative 1/8, and x minus 3. You could leave it like that. You don't have to simplify it. If you wanted to, I suppose you could. You could have y minus 15 equals negative 1/8, x plus 3/8. And then you could simplify that further. Plus 3/8 plus 15. Then you'd have to get a common denominator and add 15. So I just say just stop here. Shoot, there's no reason why you can't stop there. Nothing says you got to keep going. Okay, last thing is, so we talked about what normal means. We got to talk about find the rate of change. Okay, find the rate of change to f of x, x squared plus 2x. From a is 1 to b is 4. And let's write it like this. From 1 to 4. How about that? Can we write it like an interval? Okay, find the rate of change. Do you remember what words we put in front of rate of change to tell the difference between what kind of rate of change we were talking about? Average. There was average rate of change, so that's 1. Okay, average. And what was the other one? No, that's the same as average. Instantaneous. Hi, it is right. I still have mine from last time. Okay, bye. Okay, so watch the difference. Average versus instantaneous. Okay, average is without the limit, and instantaneous is. Okay, the average is without the limit, the instantaneous is. So let's do both. Average rate of change would be without the limit. Leibniz works really well here. So that would be f of b minus f of a over b minus a. So average does not have the limit. So that's going to be f of 4 minus f of 1 over 4 minus 1. And you're just simply plugging in. This doesn't take calculus or anything at all. We're just plugging 4 into the function. So 4 squared is 16 plus 8. So we're looking at 24 minus f of 1 is 3 over 4 minus 1. So we've got 21 over 3. So the average rate of change is 7. The instantaneous rate, that's going to be with the limit. So that'll be more like what we know of for being derivative. So if they ask you for the instantaneous rate, we already did the limit in the previous problem. So the instantaneous rate at 1 would be 2 times 1 plus 2, because that was the, I can't say derivative, that was the result that we got for the tangent slope. So that's going to come out to be 4. And the instantaneous rate at x is 4 is 2 times 4 plus 2, which is 10. So you can tell that the average rate was 7, the instantaneous rate at the beginning was lower than the average, the instantaneous rate at the end was higher than the average.